Okay. So, what I said that spectrum I can calculate. Let us say I have a sequence x of n which is the sampling version of x of at, okay, where the sampling rate is Fs. Now, what is the voltage spectrum? How do I calculate? I calculate x of n, I can calculate x of k. So, this is nothing but a voltage spectrum. So, this f is nothing but a twice pi by, you can say, the n or Fs by n into k. F is called normalized discrete frequency, normalized discrete frequency. Okay. So, x of f is nothing but, and this is the, or I can say that, let us say this is x k, instead of x of k I say x k. X k is equal to n equal to 0 to n minus 1 x of n e to the power minus j 2 pi by n into n k. That you know that. How do I do that? Okay. Now, what is small f? So, already I give you the notation in lecture week number 1 that capital F represent analog frequency, small f represent this normalized discrete frequency, which is nothing but a f by Fs. So, x of f by Fs is nothing but a Fs into this one. So, the spectrum S f by Fs is equal to x of f by Fs whole square. So, it is nothing but a Fs into x a f whole square. Understand or not? So, since it is restricted that x of a is restricted by Fs by 2, then that case it is nothing but a x of s into x of f whole square. So, that is the spectrum of the signal, voltage spectrum. Now, what is autocorrelation? Let us say Rk is the autocorrelation factor. So, I know if the x of n is infinite duration, then it is minus infinity to infinity. If it is finite duration, then n equal to 0 to n minus 1, which is nothing but the x star n multiplied by x of n plus k. This is autocorrelation. So, using Wiener-Khinchin theorem, they said the same spectrum can be calculated from the Fourier transform of the autocorrelation sequence. So, what it is said? It said that I can calculate the spectrum of a signal using two methods. One method is called direct method, computing the Fourier transform of xn. So, direct method is that I know xn, I compute using discrete Fourier transform, I compute xk, and then I can draw the k versus mod of xk curve. So, if it is energy power spectrum, it is square, I know that this square, which I discussed. Second one is called indirect method, using Wiener-Khinchin theorem, that power spectrum will be the same as Fourier transform of the autocorrelation sequence. So, I have to calculate the autocorrelation sequence Rk of a given signal xn. So, that is called step 1, and then step 2 is the Fourier transform of the autocorrelation coefficient, which is called indirect method. During LPC analysis, I also said that. So, if I calculate the spectrum, I will get this kind of value for every k, but there will be overall variation, that is called envelope. So, who is represented the envelope? Envelope is represented by the spectral parameter, or I can the system parameters, which is nothing but the Forman frequency. So, who is represented by the Forman frequency? Nothing but a LPC coefficient from LPC analysis. So, autocorrelation coefficient basically represent that envelope. So, I can calculate the spectrum of a signal using autocorrelation coefficient also. So, for deterministic signal, I can say okay, I can use direct method xn, I can take the discrete Fourier transform, I get that. But from a non-deterministic signal, random process signal. So, what is the basis assumption of when I say length Fourier length is n? We said the signal is periodic with length n, but random signal is not periodic with length n. Deterministic signal may be. So, that is why we go for autocorrelation of the signal, and from that autocorrelation we try to find out the estimate the power spectral density of the signal. Okay. So, in that case, so limiting the duration of the sequence in n points. So, I already explained that once I said that limiting that xn by a window function, that the spectrum is nothing but a convolution of window frequency response multiplied by the signal frequency response. Let us for an example, suppose I have an x of n and I take a n point DFT. So, x of n is restricted by the n point. How do I restrict it? Multiplying a rectangular window. So, rectangular window is 1 for 0 to n minus 1, elsewhere it is 0. So, it is nothing but a get function. So, if I take that Wn, this is Wn, and what should be the frequency response of the Wk, which is nothing but a sinc function. So, you know the main lobe width depends on the length of the window. If the length of the window is very wide, then the main lobe will be very sharp. If the length of the window is very narrow, then the length of the main lobe width will be very wide. So, I can say, so when it is a convolute, this response will be convolute with the original signal. So, if I say original signal has a frequency response like this one, for k equal to 1 that is there, for k equal to 2 it is there, k equal to 3 it is 0, k equal to 4 it is 0, for every k I get an frequency response, frequency value. Let us say I know it. But basically when I do the Fourier transform, I will not get this one. I will get every k, for every k I will get an Gaussian. I will get an this kind of Windows frequency, Windows convolution. So, if the main lobe width is the less, so the power of the particular frequency will be distributed to the nearby component because of the side lobe, and also if the main lobe is very wide, then there will be an overlap in nature. So, that is called DFT leakage. So, due to the DFT leakage, even the signal is deterministic, but once I make it finite length signal, then the spectral estimation is nothing but the spectrum is nothing but the convolution of the window function and frequency response of the window function and the signal. So, what I want? I want that window response should be very neglected. So, it will be neglected when that it is a narrow main lobe and very less side lobe. So, if the side lobe power is very high, that also leakage to the other component. So, I want an window function whose frequency response main lobe is very narrow and also side lobe attenuation is very high. That means, side lobe is not disturbed at next component of the signal. But getting that kind of window is very difficult. So, how do I get the narrow main lobe? By increasing n. Once I increase the n, then I know if the signal is non-stationary, then my time resolution is loose. So, I cannot increase the length of the signal. So, basically I am estimating the power spectrum. What power spectrum I am seeing, it is not original spectrum of the signal, it is in window is also in there. So, how do I eliminate that window error due to the finite length or due to the window function which is introduced? That is why it is called estimation of the power spectrum. Okay. So, now this is case of a deterministic signal. Now, let us the general problem spectral estimation. Wide sense stationary random process. So, wide stationary random process do not have that finite energy. So, E is not finite. What I said, there is two kinds of signal, one is power signal, one is energy signal. If the energy is finite, then we call energy signal. If the power is finite, then we call power signal. So, here energy is not finite, but power is finite. So, that is why I call power density spectrum or power spectrum density. Energy spectrum when the energy is finite, power spectrum when the power is finite. So, what is the mathematics of that? So, let us say Xn is a random stationary random process signal, digital signal. So, the autocorrelation x of Rk of x of n is a function of ensemble average of x of n k plus n and x of n. So, I have a non-deterministic infinite energy. I said the power is finite, but I cannot take the infinite length of the signal. I have to take the finite length of the signal. So, once I take the finite length, then automatically it becomes finite energy, but a random process is infinite energy. So, what I require an ensemble average. So, let us say autocorrelation is represent the ensemble average of the random process signal. Then using Wiener-Kinship theorem, I can say that the power spectrum is nothing but a Fourier transform of the autocorrelation function. Now, if I want to do that, then what I require the estimation of the power spectrum needs a finite autocorrelation sequence. If my Rk is infinite length, then how do I get the power spectrum? Because I cannot get that infinite length Rk. Estimation of the autocorrelation sequence required one to estimate the ensemble average function. So, if this Rk is the finite autocorrelation sequence or represent the ensemble version of the signal, then only I can say power spectrum is nothing but a Fourier transform of that autocorrelation sequence. So, that is used for power spectral estimated. So, what do we use? Estimate the autocorrelation of a random process based on a single observation of the random process. So, I have a single observation, from there I have to estimate the autocorrelation. So, achieve that we use ergodicity of the random process, which says that ensemble average can be replaced with the time average. So, this is the time average. Xn is a random signal, random process signal. From the Xn I can calculate Rk using the time average of the signal. So, time average along the n length of the signal. So, x of n is the length. So, I have a evidence random process observation of n number of sample. So, ensemble average is replaced by the time average. Once I get Rk, then I can take the Fourier transform of this Rk to get the power spectral density of the signal. Okay? So, that process. So, many common random signal are not stationary, main problem not stationary. So, suppose I have a random signal very long length, I take only this observation, but if this signal is non-stationary, so this observation is not true for all the signal. One problem. Next problem is that if my length of the observation is very high, so what is the assumption of the Fourier transform? So, I assuming the signal is stationary, but if the time length, the length of the signal is very high, during that time the signal also change the color of the properties, or properties of the signal will be changed. So, in that case that change of property will not reflect my spectral analysis. So, I have to consider that signal during this timeline the signal is stationary. So, I cannot take large amount of signal. So, that is why the finite length of the observation is very much important. So, random signal that is available in practice usually a segment, a single observation in a noisy environment. So, from there my goal is estimating the spectral content of the random process based on noisy measurement of the process that have finite set of data. So, noise is there, finite set of data is given, I have to find out the spectral estimation. There is a two methods, one is called non-parametric method, one is called parametric method. Non-parametric methods means without designing any model, parametric method means I am designing a model and then I want to estimate the power spectra. So, what are the non-parametric methods are there? So, non-parametric methods, no model parameter, no model I am used. So, what is the limitation? Estimation of the power spectrum is based on the windowed autocorrelation sequence. So, what is the meaning? Meaning is that I have an x of n. So, non-parametric, I am not modeling that x of n. So, x of n is there, I directly taking evidence of x of n by using an window function. So, I taking that measurement of x of, so finite length of x of n. So, x cap n which represent that finite version, finite length or you can the sampled version of x of n using an window function. So, windowed autocorrelation I am using. That means either I can take and then take the autocorrelation, or I can say, let us say I take the autocorrelation using ensemble time average, then I said Rk has an infinite value, R0, R1 to Rk equal to infinite. From there I am selecting a one portion only of Rk value, which is finite Rk value, which is windowed Rk value. So, windowed autocorrelation. So, that means R of n is nothing but a window version of n equal to 0 to n minus 1 it is there, elsewhere it is 0. And to estimate the power spectrum, we use a function which is called periodogram, which is defined like this way. In omega is equal to 1 by of x omega. So, what is x omega? Is nothing but a Fourier transform of xn. Okay. So, that way I can calculate the estimate that periodogram methods for non-parametric estimation of the spectrum. And it is natural to assume that if the n length of the signal is increased, then what you said, the resolution, frequency resolution is increased. So, it give me the becomes a better estimator of the power spectral density. So, instead of let us say 200 Hz, instead of 16 Hz resolution, if I have a 1 Hz resolution, then you can say I get every 1 Hz. So, the estimation is better, but it is not true. Actually, the mean of the periodogram average to the true spectral density, but in variance remain large. So, I can say if I increase n, the mean converged, but variance remain very large. So, if n increases, the periodogram tends to oscillate more rapidly. So, what is the solution they said? They said forget about that increase of n. If you have a large number of data, make it average. So, how do I make it average? Let us say xn has an observation data sequence m. M is equal to L into n. That means I have a data which can be divided L number of window of length n. So, L number of window length n point data sequence. Then for every n point data sequence, I am estimating the power spectra Ink, and then I take the average for all the window. So, taking all the data at a time, that means n is very large, that means frequency resolution is very high, but that not solve my problem. Mean will give me the true, but there will be some variance. So, to avoid that, if you have a large data, then you can divide it into n number of window, L number of window. So, suppose I have measured a long signal, 2-second signal. I said within 2-second signal I divided 200 window, and every window I have analyzed, estimate the spectrum and then take the average. That give me the better estimation of the power spectrum of the signal using non-parametric approach. There is a parametric approach, modified covariance method. So, modified covariance method block estimation the power spectra density PSD of an input using modified covariance method. What is this method? This method fits an autoregressive model to the signal by minimizing the forward and backward prediction error in the least square sense. What is the meaning? I have already discussed it during the AR model, linear prediction. AR model means only poles are there, A of Z, all pole model, autoregressive model. So, that has a backward prediction and forward prediction. So, what I am saying, whatever the signal you get, from the signal you are estimating an AR model, that means you are estimating AZ. So, you are calculating that K value, Ki value, partial reflection coefficient value. So, it is all pole model, the value specify the estimate. So, all Ki basically specify the pole position of the model. Now, from that Ki you estimate the power spectrum. So, once I get the AR model parameter, so basically what K, so if I say suppose I have an signal x of n, okay, I will take a slide here, then I will explain it. I have a signal x of n. So, I have a signal. So, what I do, I make an AR model. What is that? All pole model using linear prediction, autoregressive analysis, linear prediction. So, I can calculate the forward prediction and backward prediction. So, EIM, you know that EIM is equal to EI minus 1 m minus Ki into BI minus 1 m minus 1, forward prediction error, backward prediction error. From there, I can calculate Ki value. So, if I take the Fourier transform of all the Ki, so Ki is basically the model parameter, Ki represent the signal. And if I take the Fourier transform of the Ki parameters, then I get the spectrum of the signal. So, that is called parametric approach. So, I converted the signal. So, as if I am saying I am estimating the system which produced that signal, and then I estimating the pole, from the pole position of the system, I estimating the spectrum of the signal system. So, that spectrum basically represents the signal. So, I get the signal spectral estimation. There is another method. That method is called Borg method. So, I have already discussed Borg method, calculating Ki during the linear prediction, calculation of the Ki value using Borg method. So, what is that? Estimate the power spectral density of an input frame using a Borg method. This method fit an autoregressive model to the signal by minimizing least square forward and backward prediction error. So, instead of K forward, K backward geometric mean, they use least square, where AR parameters satisfy the Levinson-Darwin recursion, which I discussed during your linear prediction analysis. So, I will stop here spectral estimation, because if I continue that will be a very long topic. So, that again it can take another 2 to 3 week time to complete the entire spectral estimation. So, I do not want to load that course so high. So, maybe if I offer another signal processing course, So, I can explain details of this kind of spectral estimation, and they are using all kinds of things. Okay? Thank you very much.